and the first thing you did was brushing your teeth, and maybe you came out washing your hands with soap, and then you came, and if you know the health benefits, you maybe drank some lime water, and then you maybe washed your clothes, went to office, had breakfast, went to school, had breakfast, maybe a dosa, maybe some poha, maybe some rice. In all our whole day, even from the minute we wake up, we are using our new chapter today, acid, bases and salts. So I don't think the segment needed today where I tell you why you should study this chapter. This chapter is pretty much clear why we should study this. Now we use acid, bases and salts every day, bacha. From the morning we wake up till the everything we eat, everything we do, literally everything includes acid, bases and salts in some way or the other, right? The washing soda you used, the toothpaste you used, the soap you used, the dosa you ate, everything had either acid, either base or either some kind of salt in it, right? So today we are going to study this chapter from the very basic and we'll build through that so that you can top your boards in this chapter. At least it's a very important chapter, very easy, I will say. Chemical reactions and some of the chemical products that we are going to study might be a little bit difficult, but do not worry, your Aditi Ma'am is here and today we are going to ace our class 10th in this OG series. Okay, now bacha, before we start reading about actually acid and base, we should know how to differentiate them, right? How will I know that this thing is actually an acid or this thing is actually a base? Well, it's pretty much clear in a general life, but through the science view, we are diving a little bit deep into our scientific world, right? So in the science world, how do we differentiate acid from base? That is what we are going to start with. Now for that, we are going to start with indicator, right? So what is actually an indicator? What does the name suggest you? Indicator suggests you it indicates something, and in this case it indicates whether the substance we are going to test is an acid or is it a base, right? So indicator bacha is a special chemical that changes its color or smell to indicate the presence of acid or base or a chemical substance. So this in itself is a special chemical, okay, that changes its color or smell to indicate the presence of a chemical substance. That means I have an indicator. We'll study a lot about lots of indicators. Now if I put my indicator in a lime water or I put my indicator in on a soap, there will be difference in them, indicating that the lime water, that the lemon water, not the lime water, the lemon water you drank today in the morning is actually an acid, and the soap you used is typically, generally, a base. Okay, now we will study different kinds of indicators, right? First one is litmus paper. Similarly, we have litmus solution, one and same thing, mostly just a minute difference. Then we'll study methyl orange, turmeric and vanilla. Okay, so now some of the things we are going to study, which will help us to indicate whether the substance is an acid or it's a base. Okay, now one thing you do have to note, indicators which change their smell. Okay, we studied about they can change their color and smell, right? So the particular ones which change their smell in the presence of acid or base are called olfactory indicators. These are called olfactory indicators. You have to keep that in mind. It's important. Okay, some of the examples are like vanilla, onion and clove, the long we use in our everyday cooking as well. That's what a clove is, right? Now moving on, beta, let's study a bit deeper into these indicators, right? The first one is litmus. So do you see these strips? right? You must have seen them in your chemistry labs as well if you go there. So they will have like a bundle of slips, just like these strip sticky notes we have, right? The same, almost the same, they look the same, but these are in strips. So what happens whenever it's actually purple in color, okay, these litmus strips, these litmus paper is actually purple in color, okay, but when you put this purple litmus strip, or when you put this strip on acids, color in acids, then they turn from, basically if they are purple, they'll turn to red, okay. So red beta is for acid, okay, and blue is for base. Now how will you remember? Ma'am, this you don't have to tell. This B for base, B for blue. It's easy, right? Now we generally say that if I put litmus paper on acid, it will turn blue litmus to red. We just indicate, we just say it like that. Actually it is purple, but how do we write it? How do we say it? That it turns, if it was in a base first, so it will turn blue litmus into red if it's an acid, and it will turn red litmus into blue if it's a base. Understood? That's it. All clear? That's it. Okay, next beta we have methyl orange. Now it's a little tricky or something because its color is same, okay, color in acid, color in bases, it will give red and it will blue, and it's basically colorless, I guess. It's basically colorless in itself. Oh, wait, not colorless. Okay. My mind was somewhere else. Maybe it's orange. I thought I'll tell you it's clear from the name. I myself forget. Okay, so methyl orange, from the name it's clear, Aditi, from the name it's clear, bacha, it's orange. So it will also turn red when it interacts with an acid, and it will also turn blue when it interacts with a base, similar to the litmus. Okay, now bacha, we have phenolphthalein. Now ma'am, what is that? It has a weird name, first of all, and it's not my personal favorite, to be honest. Why? Because it is colorless. Okay, and when it indicates, when it tests the acid, it remains colorless. What's the point of being an indicator if you are not going to choose its color? But how is it used? If it's colorless, okay, we have two solutions, acid and base, okay, and we have phenolphthalein, right? Now if we put it in acid, it will remain colorless, but if we put it in base, it will turn pink, and very, very prominent pink, okay. So if we put phenolphthalein in our base, it will turn to pink, and hence in comparison we mostly use this so as to say, okay, this is colorless, maybe it's acid, but it turned pink, that means it's a base. Or if it does not turn pink, we can definitely say that the solution we are testing, it's not at least a base. Okay, done. Now that's 3. We have 2 more. One is vanilla extract, vanilla that we used maybe in baking cakes, maybe in shakes. That's the same vanilla it is. It's an essence, okay, and it's like, typically it's very expensive, but it's also used as an indicator, okay. So what it does, it changes its smell. So what it is an olfactory indicator. We studied about it, right? It's an olfactory indicator. So its smell in acid, it remains same, but see, vanilla has a very prominent smell, you know, and this concentrated vanilla, the extract, even has more smell. So if you put it in base, the smell will go away, and hence depicting that this particular thing is a base. Done. Okay, then we have beta onion. The onions we have in our house, yes. So smell in acids, that will remain same, the smell will remain same, but smell in bases means no smell. So typically when we cut onions in our houses as well, what we use, our hands keep on smelling like onions, right? So we go wash our hands with a basic soap, right? So what it does, it takes away all the smell, and hence onion in bases gives no smell, but onion in acids, the smell remains the same. Okay, now we will study about a universal indicator as well. So make sure you watch the video till the end, and that will definitely tell you which acid is it, and we'll study something about the strength of acid. So make sure you are watching the video till the end. Okay, now beta, this is what the whole indicators are. They tell us if this is an acid, if this thing, this chemical substance is a base. Right, now let's write the definition of acid and bases, because that's what the actual chapter is. Right, now one more thing I have to tell you, that we keep on improvising the definition of our acid and bases as we move in the chapter, because we are learning more things. We just learned about indicators, so we will specify acid and base according to indicators. Right, then we'll specify them with their strength. Right, then we'll specify them with the universal indicators. So make sure you are learning this in a calm way. We'll study 2 to 3 definitions of acid. Okay, so don't worry. Now we studied indicator. Now on the basis of indicators, let's specify what acids and bases are. Now bacha, acid, what we did on the, basically we use mostly in your labs at your level, we use litmus papers. What is this? This is your litmus paper. Now beta, if my chemical substance is turning blue litmus paper to red, blue to red, it is turning blue litmus paper to red, then bacha, this substance will be your acid, and that is the definition of acid. Chemical substances or chemical compounds whose aqueous solution, make sure you underline this word carefully, I'll tell you in a bit, aqueous solution converts blue litmus paper to red are called acids. Blue litmus paper to red are called acids. Now beta, very important thing about litmus paper is they have to have aqueous solution. They have to be in touch with aqueous solution. It should be liquidy, then only they will change the color. If you put the litmus strip on like a new soap, right, it's dry, completely dry, no water has touched it, right, if you put that litmus paper, it will not change color. But as soon as you put a drop of water on that soap, you can see it will change color. Why? Because these compounds, the chemical compounds, whether acid or base, has to be of a aqueous solution, then only it converts blue litmus to red, and these are called acids. Done. What are the main acids we use? That are HCl, okay, H2SO4, CH3COOH. Now these are something called strong acids, and this particular one is called weak acid, and this is what? This is also a nickname called acetic acid. Okay, so we'll study about this in a bit, don't worry. Basically we have strong acids, weak acids, like, right, just like everything else. We have strong humans, weak humans, and just like that we have acids, we have strength of acids. We'll study about that, but right now you can just remember we have HCl, H2SO4 and CH3COOH, some of the examples of acid. Right, now similarly, see, acid turns blue litmus to red, right? What does base do? It turns red litmus to blue, right? This aqueous solution of a base, what it does? It turns, it is again a litmus paper, right? This is again a litmus paper. Now this aqueous solution of base will turn red litmus to blue. It will turn red litmus to blue. So the chemical compound which turns, whose aqueous solution turns red litmus to blue are called, oops, these are not acids. Let me change it. Wait a second. This is called base. This is called, yep. So these are called bases. Okay, bases. Okay, done. Now these are the few examples. What are the examples? NaOH, very typical base, you'll see all the examples of bases we will be taking NaOH, because this again is a strong base, and CaOH twice, calcium hydroxide, that is sodium hydroxide, this is again a weak base, that is again a strong base. We'll study about that. Okay, so these are the few examples, these are the indicators of acid and bases, and our first definition of acid and bases. Now moving on beta, this is some of the main difference and this is important. They can ask you to differentiate between acid and bases. So first we know the very prominent, the very first difference you have to write is acids are sour in taste and bases are bitter in taste. Bitter means kadwa, right? Kadwa, and sour means khatta. So acids are sour in taste, bases are bitter in taste. Solubility in water. So acids typically are soluble in water, okay, but bases can be soluble, can be insoluble. Done. And electrical conductivity. Now acids are good conductors of electricity. Their solutions conduct electricity. Dilute solutions conduct electricity. Dilute, ma'am, what is dilute? We'll study about that, don't worry. Okay, and their dilute solutions also conduct electricity to some extent. Okay, then beta, effect on litmus paper, it converts blue to red, it converts red to blue. And touch, so acids we do not touch, okay, we do not touch acids at all, especially the concentrated ones, not even the dilute ones. Now we will study acids as well. You'll see some acids we eat as well, but ma'am, you're saying not to touch the acids. We'll study, calm down. Okay, now first of all, but still do not touch any acid. But these bases we touch every day. These are soap, and even if I tell you, even if I give you some base, let's say baking soda, okay, so beta, that if you put that and you put a drop of water, it will feel like soap, it will feel soapy. Why? Because that's the texture of bases, right? That it's feel how to touch. Okay, so that this is the main difference between acid and bases. Now moving on, we are going to study some of the chemical properties of acid and bases. Chemical properties means how do they react with other things, how do they react with metals, how do they react with non-metals, how do they react with carbonates, how do they react with each other, right? So we are going to see all of them. You can see a very colorful slide here because I want to make it fun for you, fun to remember. So this is how we are going to remember. We are going to use our visual ability to remember, right? We talked about something called picturesque memory, right? So when there are lots of colors involved, it's easier to remember the reactions, okay? And that's what we are going to do in this lecture today. Now beta, first of all, we have acids and bases. We are going to see their reactions with metals. Okay, first thing, reaction with metals. Okay, now we'll go one by one. Metals with acids and then metals with base. Let's study metals with acids first. Okay, now see, metals with acids. So what happens beta, when metals react with acids, they give salt plus hydrogen gas. When metals, learn with me, okay, when metals react with acids, they give salt plus hydrogen gas, except there are some of the exceptions, that is your copper, silver, gold, platinum, they do not react with acids. We can see if you put your gold rings or silver rings, you might not try, you should not try, but still if you put those like pure gold, pure silver in the acid, they won't corrode, they won't get bad, okay, but if you put other things, other metals, sodium or lithium, those with the acid, those in acids, you will see they will corrode, okay, they will go bad. So make sure you have this thing in your mind that if I put my silver ring or gold ring or platinum ring inside the acid, it won't go bad, okay, that's how you can remember, easy to remember, right? So beta, metals with acids give salt plus hydrogen gas. Now some of the examples, what you can take any metal, right? Let's say I'm writing the equations again, okay, so that it will be helpful for you. So you'll take zinc, okay, plus you took any acids. We studied about HCl, H2SO4, right? So we took HCl, okay, then what will happen bacha? Now we see in reactivity series, zinc is at higher place than hydrogen, right? So then means zinc will kick hydrogen out, right? So that means it is ZnCl plus hydrogen gas will be formed. Why does these things do not react? Because they are under hydrogen. That means they are not as reactive as hydrogen is. Hydrogen is more zinc is more reactive than hydrogen, so it kicks hydrogen out. But copper is less reactive than hydrogen, so hydrogen is like, I can't, you won't be able to kick me out, you are smaller than me. Okay, so then these elements are not able to kick hydrogen out, and that's how they do not react with acids. Okay, but zinc is more reactive than hydrogen, so it kicks the hydrogen out and goes sits with Cl. Done. Will you remember this? Okay, one more example we have for you. You take some other metal, sodium, okay, and you take some other acid, H2SO4. What you can see, you can clearly see we have Na2SO4. It kicks the hydrogen out and we get a hydrogen gas. Understood? Done. Now beta, we have one more thing, something called HNO3. We have nitric acid or nitric acid, if you want to call it. What happens when we add metal with HNO3? That's also an acid. So when we react metal with HNO3, we get salt, but instead of hydrogen we get water. Instead of hydrogen we get water. Now ma'am, why is that? That is because bacha, this HNO3 is a good oxidizing agent. Oxidizing agent means it oxidizes the substance. That means it adds oxygen into the other substance, right? It is a good oxidizing agent. So this is another substance, let's say our hydrogen, that's typically formed in metal with acids, right? So it oxidizes hydrogen. That means it adds oxygen with hydrogen. Now this, it adds oxygen into this hydrogen, right? Understood? So that's why whenever metals react with HNO3, they do not form hydrogen. Why? Because HNO3 is a good oxidizing agent and it oxidizes hydrogen and converting it to water. It except magnesium and manganese. So you will see there will be a lots of exceptions in chemistry and you will just have to deal with it, or you can watch the monologue of that series and you will just relate to it, and that's it. Okay, so except magnesium and manganese, for all other metals HNO3 will be converting hydrogen into water. Done. And this is one example, Zn, any metal, plus HNO3, it converts. So Zn kicks hydrogen out, right? So it converts Zn NO3 twice, zinc with NO3 twice, plus instead of hydrogen it becomes water. What is happening? H2 oxidizes, converts into water. Understood? Understood this whole slide? Metal reacts with acids to give salt plus hydrogen, except copper, platinum, gold, silver, and it gives hydrogen gas, very important point. And there is something called HNO3. If you react any metal with HNO3, it does not give hydrogen, it gives water, because it oxidizes hydrogen into water, except manganese and magnesium. You will remember it, you just need to practice. Okay, that's it. Okay, next beta we have reaction of metals, same but with bases. Now if you see that when bases react with metals, it still gives the same thing, salt and H2, but here the salt looks a little bit fishy, little bit stupid, but you just have to remember this for now, because see, they have explanation for all of this, all of these things, why these salts are being formed, but that's for higher classes. If you try to study it now, you might get confused. So just do whatever you are given, okay? And slowly if you take science, you will go into the depth of it and you'll understand why all of these things is happening, right? So for now, just cram it, okay? If you want to take science, you will understand. If you just leave science, then it's good just to cram it. Done? Okay, so we take any base, NaOH, we studied about it, and we took the same metal, zinc. Okay, what does it form? It forms Na2 Na2ZnO2. Now here only the hydrogen is released, not the OH. Okay, since, see how you can remember, in acid as well the hydrogen was released. Zn kicked only hydrogen, but there was only hydrogen to kick, right? But here they have oxygen as well and hydrogen as well, but zinc is like, no, I just want to kick hydrogen. I don't care about oxygen. Oxygen is my friend, he can stay. I just want to kick hydrogen out. Okay, so it's still, even in bases, it still kick hydrogen out. Okay, so it kicks the hydrogen out, and this is the compound that is formed, sodium zincate Na2ZnO2. Okay, and hydrogen gas is out. Again, NaOH with aluminium, similarly it just kicks the H out and not the O, so it becomes NaAlO2, sodium aluminate, right? And with the hydrogen gas, now a very big relief for all of you guys, this does not react with this basis, does not have more reactions with metals, because basis does not react with metal as common as acid does. Okay, so acid reacts with metals very easily, but bases do not. Okay, so we do not have more reactions of bases reacting with metals. So this was the first point, reaction with metals. We studied about metals with acids give salt plus hydrogen, metal with base again give salt plus hydrogen. The one thing you have to remember, in every case the metal, you can remember this, okay, the metal will kick, it will kick hydrogen out only, both in acids as well as in bases. Okay, let me write H only, not H2. Okay, it will only kick H of the metal, of the acid or base. NaOH, it will only kick out the H, and HCl, it will only kick out the H. Okay, and goes it with Cl, and here goes it with Na and O, forming sodium zincate, sodium aluminate. Okay, done, understood. This is a pretty easy way to remember this, right? Okay, now next reaction we have to study, bacha. Okay, before that, see, we talked about hydrogen, that hydrogen is being released when metals are reacting with acids and bases, right? But we need to study about some tests. Now, how do I know that this is hydrogen? Ma'am, I do the experiment and I'll just write hydrogen is released, but how will you know that hydrogen is getting released or not? So there is very prominent sound that hydrogen makes, is the pop sound. Okay, pop, pop, pop. Pop sound is the sound that hydrogen makes when it is released. So the characteristics test for hydrogen gas involves bringing a burning splint or match near the gas. So let's say you did a experiment, you can't, you shouldn't, okay, because it is not safe, so make sure you have someone elder, your teachers with you. Now then you did an experiment, and you know from this you reacted metal with base, and you know from this a pop sound, a hydrogen should be released, but how do you check it? So you take a match, you burn it, and you bring it near the beaker. Bring it near the beaker, not put it in the beaker. Okay, near the beaker, and you will see there will be a pop, 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 pop sound. Put, 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 put. Okay, so that pop sound should be heard, and if you hear that pop sound, it justifies that it has hydrogen in it. It indicates the presence of hydrogen. This pop is due to the hydrogen gas burning rapidly in the presence of oxygen. So when this hydrogen, it is going into the atmosphere, and if you bring a matchstick there, so this hydrogen reacting with oxygen in the atmosphere, right, it's burning with oxygen, so that gives that, due to that burn, we get a pop, pop, pop sound. Okay, great. Now beta, next we have the reaction with carbonates or hydrogen carbonates, or we have one more name for hydrogen carbonates, that is bicarbonate. Okay, so carbonate, or you can write bicarbonate. If you react carbonate or bicarbonate with acids, what will you get? Again, you will get a salt. Okay, we are studying acid bases, so mostly typically in product side you are going to get salt, but in this, see, remember, Carbonate is simply CO3, bicarbonate is HCO3. So wherever you see CO3, okay, wherever you see CO3 in the reactant side, you know for sure that in the reactant side you are going to get CO2. Okay, and with that you are going to get hydrogen. So what do you get with carbonate? With acid, it gives a salt plus CO2 plus H2O due to carbonate. Done. So let's take an example. We have Na2CO3, that is our carbonate. Now Na2CO3 reacts with an acid, so we took any acid, that is your HCl. Right? So Na2CO3 when reacts with HCl, what it gives? It gives a salt. What is a salt now? NaCl. It will kick the H out. Right? So it will give NaCl plus H2O plus CO2. Understood? Understood? And similarly, this is bicarbonate, right? This is bicarbonate, this was carbonate. Okay, so bicarbonate is simply putting NaHCO3 instead of Na2CO3, we have NaHCO3. Now it again reacts with HCl, it gives the same products. It gives the same products, no change. NaCl, H2O, CO2, only the balancing will change, that you have to do, right? You can do balancing, right? Take care of balancing. I put so many videos out on balancing. We took lives completely on balancing, okay? So go watch those out. There is a video on how to balance chemical reactions. You can go check that out. And you tell me in the comment section what is the balanced equation for this. This is slide number 12. Slide number 12, you can write the balanced equation. Okay. Similarly, one more example, we have carbonate of potassium carbonate. It reacts with sulfuric acid. What does it gives? Again, this kicks the hydrogen out, K2SO4, and there is carbonate, so H2O plus CO2. Understood? Okay, and a big relief for all of you, this carbonate does not react with base at all. Okay, carbonates does not react with base at all. There is no reaction of carbonates with base, so that is one thing of your table. Okay, done. Next, bacha, we have now carbon dioxide is released. So how will we understand, how will we know that carbon dioxide is getting released? So we'll do lime water test. What we'll do? Lime water test. Now we'll see, bacha, if there is CO2 and you put it in calcium hydroxide, that is CaOH twice, right? That is your slaked lime, right? Now if you put it in CaOH twice, it will give you CaCO3. It will convert into CaCO3, which is milky in color. So if anything is turning milky, that means carbon dioxide is present. Okay, and also it gives a little bit of bubbles as well. Bubbles, if bubbles are there and the substance is turning milky, that means carbon dioxide is there, and with that we have water. But there is one more thing. If you keep on passing carbon dioxide from this calcium hydroxide, you passed, it turned milky. Okay, now that is insoluble. This CaCO3 substance, it is insoluble. Okay, but you keep on passing carbon dioxide, it will dissolve again. This CaCO3 has CO2, you will keep passing CO2, but it already had water in it, right? So H2 plus CO2 again mixes with the CaCO3, that is our milky substance, and it becomes CaHCO3 twice. Now this is soluble. So what happens? This is the white precipitate of calcium carbonate, turns clear lime into milky, right? But excess carbon dioxide dissolves it again. It precipitates, CaCO3 precipitates, but if you keep on passing carbon dioxide from it, it will dissolve in this again. Okay, great. Next, beta, we have a very important reaction, and it's so important. You can take 70 to 80% chances are there that you will get at least one question from this. Okay, at least I'm saying. Done? Now, very simple. Okay, again, acid, we studied about carbonates with acid, carbonates with bases does not react, metals with acid, metals with bases. Now, beta, we are going to study acids with bases. Now what happens? Simple, the simplest reaction to exist. acid when reacts with base, it gives salt. Of course, ma'am, everything is giving salt. Yes. So everything in this chapter mostly will give salt because we call this salt. Okay. So it will give salt plus water. Okay, it will give salt plus water, just like metals did with HNO3, right? So you'll later study that HNO3 is basically an base, but we'll do that later. Okay. So whenever acid reacts with base, it gives salt plus water. That means we studied what acid is, what base is. So simply we took a very common HCl and a very common NaOH. It will give what? Again, this will kick hydrogen out and go with Cl. So it will give NaCl. This hydrogen comes here, NaCl plus H2O. The salt plus water, and this bacha is your neutralization reaction. Why? Because acid and bases are getting neutralized. We'll study in a bit, but make sure I'm saying these words. Acid and base together, they neutralize and make a salt which is neutral in nature, not acidic, not basic, neutral in nature with water. Okay, now there are few things that you can study. You can see that there is strong base, there is weak base, strong acid, weak acid, right? So if you react a strong acid with a strong base, it will give you neutral salt plus water. HCl is a strong acid, NaOH is a strong base. They both reacted, they gave you a neutral salt. Ma'am, what if we did it with strong acid and weak base? Yes, let's see. If you did it with strong acid and strong base, it will give you neutral salt. We already saw the example. HCl plus NaOH gives NaCl plus H2O. You can also take KCl. KOH. Okay, you can also take KOH, right? That's also a base. Now beta, if you take strong acid, okay ma'am, let's take HCl plus weak base. We have a weak base. We can also take some weak bases that we studied. Let's take one aluminium one. Okay, so the weak base is AlOH, AlOH thrice. So this is one of your weak bases. Okay, now what will be the reaction, bacha? What will be the reaction? This will kick the hydrogen out. Okay, listen to me. This will again kick the hydrogen out. It will become AlCl3 plus water. AlCl3. Yes, we have AlCl3 plus water, right? Now beta, if you see that this is a strong acid, right, but this is a weak base, then the salt will be neutral. No, it won't be, right? So it will be strong, it will be on the acidic side, right? Strong acid, weak base. So the salt will be towards the stronger acidic side. So we will call it acidic salt. Right? So this is what? Acidic salt. So we call it strong acid plus weak base. It is acidic salt plus water. Right? Now we can take a weak acid. What is a weak acid? See, we have studied acetic acid. What was that? That was acetic acid. That was CH3COOH, okay, plus a strong base. Can I take NaOH? NaOH was a strong base, so NaOH. Now what happens? Again, see, this will still kick hydrogen out. Okay, so what will happen? For now, I'm just telling you how to remember it, to kick hydrogen out. This just is a trick to make you remember. Okay, so this Na will go here, the hydrogen will go out, it will become CH3COONA. It will become CH3COONA. This will go with this hydrogen will go with OH to make H2O. Understood? Understood, everyone? Okay, you can also take more examples, like I'll give you a homework. There is a weak acid called H2CO3. Okay, H2CO3. If you react this with Na, what will become? What will be the reaction? What will be the product? You tell me. Okay, that is your homework. That is your homework. Very easy, not that hard. Okay, very easy, not that hard. Okay, done everyone? Now beta, the next we are moving on towards a little bit again difference between acids and salts. Now beta, we studied about indicators, right? We gave a definition of acid and bases according to those indicators. Then we studied some chemical reactions. Now it's the time to give a new definition to acid and bases. Now beta, whenever any substance is there, okay, whenever we have an acid, okay, and we put it in water, we put this acid in water, what will it give? This acid with water, bacha, will give H plus ions, and or it can also give H3O positive ions. How, ma'am? This H positive ion, this whole thing is in water, so H positive ions will be again in water, so H positive ions again react with this water present and it will become H3O positive ions. So in any case, if you see in a solution we have hydrogen plus ions, H plus ions, or H3O plus ions, that means that solution has acid in nature, acid in it, or it has acidic nature. Done. Now beta, same if we put bases with water, if we put bases in water, what will we see? We will see that base in water, it is giving OH negative ions, OH negative ions. So anywhere you see there are OH negative ions in a solution, that solution is base, has base in it, it is of basic nature, right? Now this is called hydroxide ion, OH negative hydroxide. That's why we keep calling sodium hydroxide. Remember, we said NaOH, it has OH ions, right? That's why it was called sodium hydroxide, right? So it is hydroxide ion. However, H3O positive, this is called hydronium ion. This H3O positive, not H positive, H3O positive is called hydronium ions. OH negative are called hydroxide ions. Understood? Okay. Next beta, moving on, we have some types of acid. See, we are again and again I am saying there are strong acid, weak acid, strong base, weak base. So let's study about this. Okay, so we studied about that they give H positive ions, OH negative ions, H3O positive ions, right? That means in science we call that dissociation. That means in science we call it as dissociation. That means bacha, acid is going into water, okay? Acid is going into water and it is dissociating into its ions, which include H positive ions. Understood? So acids which dissociate completely and rapidly or readily, they dissociate completely and readily gives H positive ions are called strong acids, like HCl, like H2SO4. These are strong acids because they completely dissociate into H plus and Cl negative ions. They completely dissociates into H positive, SO4 2 negative ions. So this H positive, it is completely and readily given in the solution. Okay, so these are called strong acids which do not give readily. Okay, they partly dissociate in water. Okay, slowly, not completely, not all the HCl molecules dissociate into H plus and Cl negative. So they partly dissociate in ion, and all of them do not give H positive ones, ions, right, are called weak acid. What are the weak acids? We studied CH3COOH, right? That is your weak acid. That was called acetic acid, right? We have oxalic acid. We have citric acid. Okay, so these are all the acids which are weak in nature, and beta we eat these acids. These acids we should not touch. We should not touch HCl, H2SO4 at all, not even the dilute solutions. But these acids, these are the ones we eat. Citric acid we get in oranges, right? Oxalic acid we get in tomatoes, we eat that, right? So that is how these are. There are different types, they are present in different places. Some will burn a hole on our skin, and some we eat ourselves. Okay, that is the range of acids. Just fascinated by it. Okay, next beta we have based on origin. So acids which are synthesized or extracted from minerals are called mineral acids, right? They are called mineral acids. And acids which are extracted from plants and animals. Plants and animals are called organic acids. Again, oxalic acid from tomato and citric acid from fruits, right? So all these will be organic acids. From minerals, if we extract some acids, those are called mineral acids. Understood? Understood? Okay beta, great. Now types of bases, right? So bases are simply of two types. Now bases can be soluble in water and they can be insoluble. This is the first, remember the first difference we studied for acids and bases. What did we say? That the acids are always soluble in water. Bases can be soluble, can be insoluble, right? So there are two types of bases. What are those? Soluble bases, water soluble bases, water insoluble bases. Now water soluble bases are also called strong base. Water insoluble are also called weak base. That's one thing you have to remember. And beta, the bases which are soluble in water are called alkalis. They are called alkalis, right? Or water soluble bases. Then we have insoluble, those bases which are partly soluble, okay, which settles down, which do not dissolve in water, are called water insoluble bases. These are simply NaOH, KOH, all the strong bases. These are all the weak bases. NH4OH, NH3, all these are weak bases. Understood? Understood? If you have any doubt, you can ask me in the comment section. CaOH twice, CaOH twice is also a weak base. Okay, so all these are weak bases, all these are strong bases. Done. Next beta, let's move on to a very important differentiation or a very important point. See, I am telling you again and again that do not touch a strong acid. Okay, not at least the concentrated ones. So what is concentrated? What is dilute? So we talked about concentration, right? You know, concentration, we have studied it in 9th class. So based on the concentration of acid in water, what? Based on the concentration of acid or base, in water, they are classified into either concentrated base or concentrated acid, or dilute acid or dilute base. Okay, see, concentrated acid or bases are what? Acids and bases with minimum amount of water. We take a tube, okay, we take a beaker, and in that I tell you it has concentrated acid. That means the amount of acid is so much more and the amount of water is a little bit. So that is a harmful acid, right? That is harmful for us, okay, because it is acid, it will burn your skin and there is no water to cool it down. Okay, so that is a concentrated acid or base, right? Next beta, we have the symbol for this is concentrated HCl or C in the bracket HCl. Now dilute is the reverse of that. Dilute acid or bases with more amount of water than the minimum amount required. We have more water than the minimum amount required. That is your dilute acid and bases. Dilute acid and bases are not that harmful. That's why we always wear lab coats, so that if some acid falls on our coat, it should not fall on our skin first, right? And by your level you will be using dilute acid or bases. They are not that harmful, but still harmful. It can cause rashes, burning. Okay, so make sure you are very careful. Now its symbol is simply dil, heart, DIL, and simply a D in front of HCl. So same, HCl is dilute as well, HCl is concentrated HCl. This HCl is very, very, very harmful. This HCl is also harmful, but not that much. Okay, great. Now beta, moving on, we have one important thing, that is your a very important study that says that you want to make a you have a concentrated acid, you want to convert it to dilute. Okay ma'am, I'll just add water into the acid. You know what will happen? A blast will happen in your lab. So if you have a beaker, okay, if you have a beaker and you have lots of acid in it, lots of acid, and you took one dropper and you're putting water, you are putting water in it, beta, there will be a big explosion. There will be a big explosion. Do not do this. Do not do this at all. So we should not add water in acid. We should not add. Okay, this should not be done. What has to be done? You take a beaker of water. Okay, you take a beaker of water in which you have lots of water in it. You have water in it, and you take a dropper and you put one drops of acid in it. You put one drops of acid in it. So there is big amount of water, small amount of acid. It will absorb all the heat. Water can absorb heat, right? So it will all absorb all the heat from this concentrated acid, and now there is lots of water, small amount of acid. It is now dilute, right? But this is concentrated acid, which should not be done. So while diluting acid, water should not be added to acids, but we should add acid in water, acid in water, gradually, slowly, because dilution is highly exothermic. When you dilute something, when you dilute acids, it will give so much heat out, and water in acid may cause accidents. There is so much water, so much acid, small water. Will it be able to absorb the heat released? No, it won't be, right? So that's how we should dilute some acids. Okay, next beta, we have some questions for you. Yes, finally my day has come. Let's do some questions. Very easy. Okay, very easy. Do not worry at all. What is observed when 2 ml of dilute hydrochloric acid is added to 1 gram of sodium carbonate? Okay, so ignore these amounts for now. You will study in the first chapter of +1, right? But for now, don't. So just ignore this. Okay, ignore this. What is dilute hydrochloric acid? That is your HCl, right? Added to 1 gram of sodium carbonate. What is sodium carbonate, bacha? Na2CO3. Okay, and taken in a clean and dry test tube. Write the chemical equation for the following reaction involved. So if you can see beta, this is slide number 22. Okay, slide number 22. Write down the answers in the comments. Okay, let me know, have you written the answers? I'll give you 1 second, write the answers, and after that I'll give you the exact the answer to this. Okay, do not worry. Done? Okay, now beta, you see one very important thing we studied. Very important thing we studied was what? Whenever you have CO3, whenever you have CO3 in the reactant side, you will definitely get what? You will definitely get CO2 plus water in the products, plus water in the products. So what is left? Beta, salt will be made. What salt will be made? It will kick the hydrogen out, right? So it will be simply NaCl. Understood? Understood? The way we studied, did you understand? It will kick that, whatever you see an acid. Oh, it will kick the hydrogen out. What will kick the hydrogen out? Obviously the metal. Okay, obviously the metal. So Na kick the hydrogen out, it becomes NaCl, and ma'am, we have CO3. You told that whenever you have CO3 on the reactant side, CO2 and H2O will be made, right? Now what will you observe? They have asked. So we have CO2, right? We will observe bubbles, correct? We will observe bubbles, and beta we have water coming out as the byproduct, right? So it is an endothermic reaction. Endothermic reaction. That means you will see that after you add these two, the temperature of the beaker will what do you say? The temperature of the beaker will come down. Okay, so that is what we have. Bubbles of CO2, endothermic reaction. The equation is HCl. Na2CO3 gives NaCl plus CO2 plus H2O. Balance this chemical reaction. Okay, let's see if it's balanced. H is 1, H is 2 here. We don't balance H first, we balance metals first. So Na is 2 here. Okay, let's balance this. Na is 2 here, Na is 1 here. So let's just add 1, 2 here. Okay, now we have C. C is 1 here, C is 1 here. Now we have chlorine, right? Non-metal. Chlorine is 1 here, chlorine is 2 here. So we'll add 2 here. Now hydrogen is 2, hydrogen is 2. Oxygen is 3, oxygen is 2 here. Oh shit, what will we do? We'll have to balance this whole again. So we'll do 1, 2 here. We'll do 1, 3 here. Okay, ma'am. Now sodium is what? It becomes 4. So we'll have to add 4 here. Now Cl is 4 here. Again, ma'am, we'll have to add 4 here. Now 4 hydrogen, 2 will be here. Right? So you do this. Okay? You do this and let me know the answer in the comment section. Oh, maybe I did some mistake. Okay, the oxygen was here as well. Okay, let's do it. We have 2 sodiums. We have 2 sodiums here. Okay? Next we have Cl. We have 2 Cl here now. So here we should add 2 Cl. Carbon is same, and we have 2 hydrogen, 2 hydrogen. Oxygen is 3, oxygen. It was balanced. Sorry, my mistake. It was balanced. Okay, very good. Next, that's why I was saying, what is this? This is not balancing. Okay, next beta, we have a question. Name the indicator that is extracted from lichen or lichen, whatever you want to call it, plant. So beta, just remember lichen is L, that is basically your litmus, but this is not litmus paper, it is litmus solution, and from that we convert this litmus solution into litmus paper. So your actual answer will be litmus solution. Okay, this will be your answer. Done? Okay, next question we have, what will happen to blue litmus when it is added to soda water? Now, what is soda water? Acidic or basic? Remember that Coca-Cola you just drank yesterday? That beta, that is soda, that has carbon dioxide in it, right? So carbon dioxide, when reacts with water, it form an acid, that is your carbonic acid. H2CO3, right? Now this is acid, so it will turn blue litmus to red. It will turn blue litmus to red. We have, see, soda water is acidic, so CO2 plus H2O, it gives H2CO3, that is your carbonic acid, so it will turn blue litmus to red. Understood? Okay, next beta we have, this is an MCQ kind of thing. So study the following table and choose the correct option. We have salt as NaCl, that is your sodium chloride, sodium carbonate Na2CO3, sodium sulfate, that is Na2SO4, sodium acetate CH3COONA. Okay, ma'am, how do you remember this? Because ma'am is studying chemistry from years now. Okay, so this is your NaCl, this is your Na2CO3, this is your Na2SO4, and this is your CH3COONA, right? Now beta, how do you see? This is a salt, right? This is a salt, and we know salt is basically in neutralization reaction we are given acid and base, right? So salt is made up of acid and base is acid plus base gives salt and water. Now if we are given a salt, can we see which acid is this? Okay, so basically what you do is you have NaCl, right? To see its salt, you take this metal and you put it with, see, NaCl, this Cl will be HCl acid, okay, and this sodium, this will be base, right? So you take this NaOH. So this will be its parent acid and parent base, right? Parent acid, parent base. Now see, both are strong. This acid is also strong. So will the nature of salt be basic? No, it will be neutral, right? This will be neutral and not basic, because strong and strong are adding up. Strong and strong acid, neutral. Strong and weak base, acidic salt. Base, weak acid and strong base, basic salt. Weak acid, weak base, neutral. Okay? Sorry. Now beta, we have Na2CO3. So we have H2CO3. Now this is, ma'am, a weak acid. NaOH still a strong base. This is weak, this is strong. How can this be neutral? This will be a basic salt. This will be a basic salt. Next beta, we have sodium sulfate, H2SO4 and NaOH. This is strong, this is strong. So this will be neutral. Oops, but this is acidic. Written is acidic. So this is also wrong. This is neutral. This is also wrong, right? Next we have sodium acetate, CH3COOH. Okay, ma'am, this is a weak base and this is a strong, this is a weak acid. This is a strong base. So this should be weak. This is be basic salt, right? So this is basic salt. So this will be basic salt and this will, bacha, will be your answer. So option 4th, D is the correct option. Understood how we did all this? Understood? Okay. Let's move on to the next part, beta. We have strength of acids and bases. Now, I was talking to you about strong acid and strong base, right? So we said that whatever dissociates in water is a strong acid, whatever does not dissociate in water completely is a strong base. But we still don't know exactly how strong it is. It is too strong, it is mildly strong, or not strong at all. How strong is the base? Too strong, mildly strong, and not strong at all, right? So that is where we take in the concept of pH scale or pH values. Okay, pH beta simply is called potential or power of H plus ions. It is simply a power of H plus ions. So it's basically a scale. Okay, I will show you the scale first. Okay, this is the scale. Okay, it has numbering from 0 to 14. Okay, and midway we have 7. So beta, 7 is what? 7 is neutral. Okay, 0 to 7. 0 to 7, this range, if anything comes in this range, that thing will be acidic. If anything comes in the range of 7 to 14, 7 to 14, or let's say 8 to 14, 0 to 6, you can call that as well. Okay, this will be basic. Okay, so basically bacha, the pH is the power of H positive ions. They will ask you the definition. Okay, so pH is the potential or power of H positive ions. Done. It is the degree to measure acidic and basic strength, to how much degree the substance is acidic or it is basic, right? So that is the degree of strength of acid and bases. Done. So this value ranges from 0 to 14. It's a pH scale and the value ranges from 0 to 14. Done. Now beta, if the pH is less than 7, it is acidic. It is acidic. Okay, if the pH is equal to 7, then this is simply neutral, we call it, or we call it water. Okay, we call it water. Why we don't call it water? Water has a pH of 7, right? That's why it is neutral. It is not acid, it is not basic. Done. Then beta, we have pH greater than 7. That will be your basic, or that will be your base. This is basic or base solution. Now what we have to study? We have to study a very important concept beta. That is what? That is your how the pH actually varies with acid. Okay, so see, the more we go on this lesser number sides, the more we go on the red side, it will be more stronger acid. This will be a strong acid. This will be a strong acid. Okay, this will be a weak acid. Okay, weak acid, and this will be bacha your strong acid. Okay, now similarly, if you go on this side, then the basic strength, see, that means, see carefully, now pH is decreasing, right? pH is decreasing, so pH bacha is decreasing. That means acidic strength is what? It is increasing. Understood this one thing? As we go towards 0, the acid is getting stronger, right? So pH is decreasing, acidic strength is increasing. pH is decreasing, acidic strength is increasing. On the other hand, that means we can say that pH is inversely proportional to acidic strength. Lesser the pH, more the acidic strength. Lesser the pH, more the acidity. More the pH, less the acidity. Great. Then it is directly proportional to basic strength. That means as we go towards the 14, now this is a strong base. This is a strong base, beta. This is a strong base, and this is your weak base. This is your weak base. Understood? So more the pH, more the basicity. More the basic strength, less the pH, less the basicity, less the basic strength. Okay? Understood? That's mostly it. What you just have to study is this universal indicator. It's the best indicator hands down to ever exist. Okay, now universal indicator beta is a mixture of different kind of indicators. We will not go into the detail in this class. Okay, first, now universal indicator is a mixture of different indicators that shows different colors at different pH values and is used to determine the strength of acid and bases. That means you have a universal indicator, you have an acid. Now if you mix them, if you put the universal indicator in the acid, it will turn into one of these colors. If it turns into bright red, it is a strong acid. Less red, a less strong acid. Maybe yellow, then the pH of that substance is 4. Okay, then maybe greenish, 5. 6, if it turns into green or greenish blue, then that's water. That means that's neutral. If it go towards darker blue or purple shades, that means it's a strong base. So it eventually tells us how strong the acid is, how strong the base is, if it's a weak acid, weak base, if it's a neutral substance. Done? That is a universal indicator. It is for us, beta, right? And you can understand how important that is to indicate the exact pH, the exact acidic strength of a substance, of an acid or a base. Done? Okay, now beta, moving on, we have importance of pH in daily life. Questions will come from this. This is very important and few questions will definitely come from this in your board exams. Okay, so read this very carefully. This is something you just have to understand how pH is used in daily life. Okay, not some very hard chemistry in this. Done? Now beta, our human body, see, we have acid in our stomach, HCl. If you studied life processes, one shot is uploaded, you can see. If you study that chapter, you see that our stomach has HCl in it. That is very, very acidic in strength. But we do not get harmed by this, right? Because that is protected by mucus, a lining in the stomach, right? But normally we need water. Water is neutral. So our body operates in a scale of 7 to 7.8 pH. Okay, that is important. Living organisms can survive only in this narrow range of pH change. Okay, so if we drink lime water, we drink Coca-Cola, still all these lies in this simple range. Okay, less than this will be so acidic, more than this will be so basic, not suitable for our human body. Okay, now beta, acid rains. We have heard about acid rains. They can cause harm in aquatic plants and animals because it is too acidic. Okay, acidic rain, pH is very less. Okay, that's why farmers sprinkle base on them. Some pesticides and all, they have base in it. So farmers sprinkle base on that their crops after acid rain, because more acidic will harm them. So they sprinkle base, it takes them back to the neutral point. Done. Then beta, pH change in soil. This is also important. Plants require certain pH soil for healthy growth. pH value varies within the type of plant and soil. Done. Next beta, we have pH in a digestive system. HCl released in our stomach and it helps in digesting food and kills some bacteria, some pathogens present in our food. But sometimes excess of acid is released by stomach and causes acidity. You have seen a lot of people telling I'm getting acidity. Why? Because a lot of acid has been produced and our stomach lining is not able to protect us from that. So it comes up, okay, it comes in your esophagus, and when it comes in your esophagus, esophagus is not bad, does not have that protective lining, right? So it comes out, so it feels like burning. Of course, if acid comes in your stomach, if acid comes in your body, it burns, right? And just again for now beta, if you, this is a bit too much, but still if you eat a lot of the stuff outside, basically oily and these chips and all, so it creates so much acid in your stomach, right? There is something called acid reflux, so it starts coming into your esophagus, and if you do it a lot, your esophagus will get bad, it will get hurt from this acid, right? It can develop ulcers, and a lot of the cases has been there for esophagus cancer, and that's because of all the burgers and pizzas that we eat regularly. Okay, I'm not scaring you away, okay, I am, because you should not, but it's not that you should completely like stop it, but you should go for walks, you should see that the acid is regulated, you should not eat that much acidic things, okay, and you should maybe get some antacids and all, and eat some basic things as well to neutralize the acid in your stomach, okay. So that's why, coming to that point, there are so many medicines. Whenever we get acid reflux, now there is acid, we want to neutralize it, what will we do? We'll add base, right? So this base, the medicines we take for acidity are simply bases. These are what? These are antacids, medicines which are edible bases. These are edible bases and neutralize excess acid in a stomach. Like eno lo 6 seconds mein kaam shuru, right? So what it does, it neutralizes the acid in our body because it itself is a base, okay. Some examples are NaHCO3, MgOH twice, magnesium hydroxide. These are all bases, okay. Sodium hydrogen carbonate, we'll study about this in a minute, that is baking soda, okay. So all of these are bases and helps to neutralize the acid in our stomach. Done. Next beta, we have our tooth. Now beta, our tooth actually, they operate at a lower pH. So what happens? pH change as the changes cause tooth decay. Why? Tooth decay starts when the pH of the mouth is lower than 5.5. In our mouth actually it's a little bit acidic, okay, and our teeth are surviving that, right? But if it goes even smaller, even lesser than 5.5, that's a thing you can learn. These teeth, the tooth enamel, the covering on the teeth, that is your enamel, made up of calcium phosphate, is the hardest substance in the body. This is your hardest substance, and in the pH less than 5.5 it starts to decay, okay. It does not dissolve in water but is corroded when the pH in the mouth is below 5.5. Bacteria present in the mouth produce acids by degradation of sugar and food particles. So whenever you eat sweets in the night and you go to sleep without brushing, what happens now? Bacteria comes, okay, and it releases some substances that is acid, okay, and due to those acids beta, you don't get cavity because of bacteria, you get cavity because of the things they released, that is the acids. So you get cavity. What are the cavities? Cavities are your destroyed tooth, the enamel gets destroyed, right? So that is what happens actually in your teeth, okay. So make sure you are brushing your teeth. See, these are producing acids. So what will you do? You will use toothpaste, which is basic in nature. So it neutralizes and you are protected from bacteria. Okay. Then beta, we have self-defense by animals and plants through chemical warfare. So actually, if you see here, I was gotten stung by a bee 2 or 3 days back. So what happened? It releases acids in your body and it was so stingy, it was so painful, I kid you not. So what happens? They release these acids because of to protect themselves. Actually, it was just sitting on a railing, right? I was going down and I was holding that railing, and I think I pressed my hand on it, right? So it stung me. So self-defense by animal and plants through chemical warfare. Bee sting leaves an acid which causes pain and irritation. Use of mild base like baking soda on the stung area gives relief. Stinging hairs of nettle leaves inject methanoic acid. This is the main thing. So what happens? These bees, these leaves, there is a plant called nettle leaves, right? So if you touch this, you will again feel a very stingy feeling. That is your acid released in your body, that is methanoic acid or methanoic acid. This is important. It's a methanoic acid and it causes burning pain, and they do it for their own protection. Okay. Okay, next beta we have, these are some naturally occurring acids. I told you, right? We have vinegar. Acetic acid is present in vinegar. We drink it a lot. Orange fruit, it has citric acid. Tamarind, we have tartaric acid. Tomato, we have oxalic acid. Curd, we have lactic acid. Lemon, we have again citric acid. And sting, we have methanoic acid. Nettle sting, we have methanoic acid. Okay, see, these still stings, right? But all these we eat and these stings. So see the range of it. Okay, see this range of acids. Okay, next beta we have some questions. You have two solutions A and B. Okay ma'am, we have two solutions A and B. The pH of solution A is 6. What is the pH? It has 6 and it has 8. Okay, which solution has more hydrogen ions? Arey baba, what have they asked? So see, beta, we studied that pH scale. It says that 7 is neutral. From greater than 7, all are bases. Less than 7, all are acids. So these are acids. Okay, and these are bases. Right? Which of this is acidic and which one is basic? We already told. So this is neutral. 7 is neutral. A is acidic in nature. B is basic in nature. Understood? Easy question. Okay. Next we have fresh milk has pH of 6. How do you think pH will change as it turns into curd? So beta, see, curd has lactic acid. Okay. Now milk beta, milk when turns to curd, it becomes acidic. Why? Because curd has lactic acid in it. That's why it turns acidic. So pH will decrease. When milk is turned into curd. Right? Explain your answer. Because of lactic acid. So see, pH of milk decreases as it turns into curd because bacteria produce lactic acid during curd formation, making the medium more acidic. Hence the pH becomes lower than 6. Okay, done beta. Okay, next beta we have common salt. Oh, we are finally on to the final phase of our chapters. We are going to see some substances. These are going to be a little bit difficult to remember. I am not sugarcoating this, okay, that I will teach you in some way that you will never forget. You will forget, okay, but you will remember these with what? With one mantra, that is beta, practice. Some of these are easy. NaCl, common salt, it's easy. Okay, you don't have to remember much of it, but some of these are a little bit difficult, not that much, little bit difficult, and that also you can learn with practice. Understood? Okay, now beta, common salt, very basic. It's a raw material for chemicals, right? So this chemical formula is NaCl, sodium chloride. How it is prepared? So one thing is you can prepare it with C. From C, you take sea water and you evaporate it. All the water is evaporated and there is some salt left, and that is how NaCl is made. And one is lab method. So we studied this, right? HCl plus NaOH becomes NaCl plus H2O, right? Now beta, this is not feasible. Okay, first it is made up from these acids and bases and chemicals, right? But it's very expensive. It is very expensive. So this is the main way to go. We evaporate the seawater. Okay, what are the uses? It is used as table salt in food. Our body needs it, right? Our body needs, and along with NaCl, it has we need water, right? We says to protect from dehydration. Why? Water retention. Water has all these minerals, magnesium, sodium, chlorine. So our body actually needs these chemicals, right? NaCl, we need it as raw products for several chemicals like NaOH, Na2CO3, NaHCO3. These are we are going to study in the next slide. Okay, this is easy, right? Let's move quickly to the next side. Is your caustic soda, that is your NaOH. Caustic soda, whatever you want. NaOH, NaCl, we move to NaOH, right? What's the chemical formula? NaOH, sodium hydroxide. Now beta, how is this prepared? See, when electricity is passed through a solution of water and common salt. So what we do, we take water, we take a beaker, okay, we take a beaker, and in that we take NaCl, our common salt, and water, okay, and we put two rods in it. We put 2 rods in that. This is, wait, oops, yes, we put 2 rods in this solution, okay, 2 rods in this solution. One is anode beta, one is your cathode. Now how I told you to remember this? We add NaCl plus H2O. Now I told you that A comes first, so it has positive charge, and C comes last, so it has negative charge. That only you can remember. Now beta, it has NaCl and H2O. We pass electricity. We pass electricity through these rods. These are connected with the external batteries. We pass this electricity from these 2 rods, and what happens when NaCl and H2O, it breaks into ions and it switches. The Na goes with OH and H comes with the Cl, okay. So NaOH is made, okay, and with that Cl2, okay, not acid is made, Cl2 is made, and hydrogen gas is made, okay. So Cl2 is produced at anode. See, Cl2 is negative, H2 is always positive, that you can remember. So Cl2, the negative part goes towards the anode, so Cl2 deposits at anode and hydrogen gas deposits at cathode. So Cl2 is produced at anode, H2 is produced at cathode, and with that we get our caustic soda. That's what our main product was. That is what our main product was, okay. This process is called chloralkali. This process beta is called chloralkali. It has chlor in it, so it is called chloralkali. That's how you can remember. Due to the formation of chlorine, okay, so it's basically because chlorine is formed and an alkali is formed, that is your NaOH. So NaOH is your alkali, Cl is your chlorine. Both of these together are called chloralkali process. Done? Okay, moving to next, what are the uses of NaOH? So NaOH, that is our, again, what? It is our caustic soda. NaOH. First we studied NaCl, then we'll study NaOH. NaOH is caustic soda. So it is used in making detergents and soaps, okay. It's a base, okay. We know that this is a base. So the first use is what? Soaps, okay, in paper making, in bleach manufacturing, okay, in extraction of aluminium metal. These are the some things you have to remember, okay. Now hydrogen beta, hydrogen is a fuel. We all know that it can used in making HCl, hydrogen reacting with chlorine, HCl will be made, and making fertilizer, that is your ammonia, okay. Then chlorine beta, chlorine we know it is used to purify water in water treatment plants, in swimming pools. We know they say that it has chlorine in it, right? So it is used to process and purify water. In making PVCs, right? Polyvinyl chlorides, PVC sheets we use, right? Making disinfectants and CFCs, chlorofluorocarbons, we'll study about that. And also in making pesticides. Okay, then beta, next we have bleaching powder. We just studied that it is used to manufacture bleach, right? In bleach manufacture. So like related. NaCl we studied, then we used NaCl, okay, then we used NaCl with water to make NaOH. Next beta, this NaOH is used to make bleaching powder. How? So NaOH beta, this bleaching powder, okay, so NaOH you can use, that's a different thing. From here we are going to use ClOH twice. See, Na is sodium, calcium is also Ca is calcium, and they are both metals, okay, so they are together, okay, but they are in the same like adjacent groups of the periodic table, right? So this, instead of NaOH, you can remember we use calcium, but we have calcium as 2+, so it will be CaOH twice. So this bleaching powder, see how you connected, I'll explain again. NaCl we studied, okay, from NaCl we made NaOH. From NaOH, all you have to do, just cancel the Na, put calcium instead of Na, CaOH twice, calcium hydroxide instead of sodium hydroxide. That is used to for bleaching powder, okay, making bleaching powder. Now how will that happen? See, first you remember the formula, okay, that is what? CaClO twice, that is your CaClO twice, calcium oxychloride, CaClO twice, calcium oxychloride. Now how will we do it? By passing chlorine gas on dry slaked lime. On dry slaked lime. What is slaked lime? CaOH twice, it is your slaked lime. CaOH twice, we studied in the last chapter as well, it is your slaked lime. So we do what? CaOH twice, we passed chlorine. See, we need chlorine here, we have CaOH and the formula is CaClO2, so we need Cl, right? So we pass chlorine. What happens? This calcium, this Cl goes and sits with what? Calcium and oxide, and again it kicks hydrogen out. This is just to remember, okay? Again it kicks hydrogen out, so it sits on the place of H. That's it. So CaClO twice it becomes. So what I'm trying to say is CaOH twice, when Cl2, it goes and sits with hydrogen on the place of hydrogen, CaOCl twice. That's the only difference. There is whole twice. Here also we have whole twice. Yeah, that's true. Okay. And with that, this also gives us CaCl2 and H2O. Okay, that's the thing you have to remember. It also gives CaCl2 plus H2O. Main thing is what? This Cl2 is kicking the hydrogen out. CaOCl2 or CaClO2 whole twice is your final answer. And with that, this calcium also reacts with chlorine. So CaCl2 plus water is being made. Okay. Now beta, bleaching powder is also called chloride of lime because chlorine is added in lime, right? So it's called chloride of lime. Understood? And what are the uses for bleaching cotton and linen in the textile industry? See, when we see that cotton is actually a little yellowish in color, to make it white, that is to bleach it, we use bleaching powder. Okay, for bleaching wood pulp in paper factory, wood pulps again yellowish in color, we need white papers, right? We need white papers, so we bleach them. Acts as an oxidizing agent in the chemical factories for disinfecting drinking water as well. Okay, done. Now next beta, very important thing is your baking soda. Now again it is simply NaHCO3. NaHCO3, sodium hydrogen carbonate or sodium bicarbonate, that is your baking soda, NaHCO3. How will you remember this? Practice, practice, practice. Okay, done. Now, how will you make this? Now we studied common salt, right? And in the properties of common salt, beta, we studied that is used as raw product for several chemicals like NaOH. So we made NaOH from NaCl, right? Now it is also used for raw product as NaHCO3, that is your baking soda. NaHCO3 made from NaCl. How? That is what we have to figure out. Okay. Now, beta, remember one thing, NaHCO3, now it has CO3 in it, okay? So remember from where CO3 will come? From CO2 and a water, just like we studied in the previous reaction. We studied that CO3 is in reactant, so the product will be CO2 and H2O. But ulta is also, reverse is also true, right? So if CO2 and water is in reactant, the final product can have CO3 in it, right? So we need CO3. From where will we get? H2O and CO2. H2O and CO2. So we know we need NaCl, right? Just remember this formula and the reaction will be very easy. You want to make NaOH CO3. Na we get from NaCl. Okay. CO3 we get from CO2 and H2O. And H beta, just remember, we will get from ammonia or NH3. Understood? Crazy, right? Similarly, we did here. Right? I need CaClO twice. How will you remember? I need Ca and O. I will get that CaClO twice. So I will get Ca from CaOH twice, right? O is generally there. For Cl, I will add simply chlorine gas, right? Understood? Okay, next beta, we are doing this. So NaHCO3, just remember this. We will get Na from NaCl, H from NH3, CO3 from CO2 and H2O. And the final product is NaHCO3. And this NH3 reacts with this Cl. This Cl comes out, right? This Cl, and we'll get a product NH4Cl. Okay, that's a byproduct. So, chemical properties of NaHCO3. NaHCO3 is basic in nature, beta. It's a baking soda and it is basic in nature. Okay, as heated, it decomposes into. When you heat NaHCO3, it's a base. What it will do? It will heat, right? And it will leave out this hydrogen, right? Na2CO3 will become Na2CO3 and CO3 is here. Come on. So it will give CO2 plus H2O and we heated it. Yes. Okay. So CO3 will give CO2 plus H2O and H will go out and we'll have Na2CO3 as our product. Na2CO3 is our washing soda, which we are going to study in the next slide. Okay. Now beta, this when you add this baking soda with tartaric acid, that is your edible acid. Okay, tartaric acid we got from tamarind. Remember, we got this acid from tamarind, right? So from tartaric acid, if we add baking soda in tartaric acid, we are going to get baking powder. Okay, and this baking soda is NaHCO3, so we'll again get CO2 plus H2O. Okay. Now for making baking powder, which is a mixture of baking soda and a mild edible acid, that is your tartaric acid. Now when baking soda is heated, it is mixed with water. Okay, the following reaction takes place. We know it heats, it becomes Na2CO3 plus H2O plus CO2 due to this CO3. Done? Then CO2 produced during the reaction causes bread or cake to rise. Now is the question comes, why baking soda or baking powder, maybe baking soda is added in cakes, added in whatever substances we need them to bake, to rise. Okay, we add it in dosas somewhere, or we add it in dhoklas, we add it in chole bhatures, right? Oof, I'm so missing chole bhatures right now. Okay, so whatever happens beta, this NaHCO3 is added in your cake. It goes in oven, it is heated, right? When it is heated, what is happening? Na2CO3 is becoming, but we are getting H2O and CO2. Now CO2 form bubbles. We remember CO2 form bubbles, right? And CO2 is heated. So CO2 is forming bubbles and it wants to come out. It's trapped inside the cake. It wants to come out. It's like, hey, hut, let me go out. So it makes them rise. Okay, in the attempt of coming out, in the attempt of CO2 coming out of your cakes, out of your dhoklas, it fluffs them up. Okay, making them soft and spongy. Done. Also used as antacids, okay, and is basic in nature. So it's a base. It's also used in antacids, as antacids. Also used in soda acid fire extinguishers. So earlier it was used that in fire extinguishers we need CO2, right? To reduce the, not reduce, to cut the supply of oxygen, we need CO2. So we used to take baking soda in fire extinguishers, and when we, in the case of fire, we put that fire extinguisher out and it heats up, okay, and CO2 is released, and that's why it cuts the supply of oxygen, right? Done. But right now we have new technologies in which we can directly put CO2 inside the fire extinguishers and we can use it whenever we want. I hope not. Okay, next and the last beta is your washing soda. Now chemical name Na2CO3. We make it from heating of NaHCO3 is heated, Na2CO3 is being made. Easy. Okay, so Na2CO3 dot 10H2O, that's it. Washing soda, washing from water, so you just add extra water, that's how you remember it. Okay, dot 10H2O, that is your sodium carbonate decahydrate. Hydrate is for water, deca is for 10. 10H2O will be your decahydrate. Okay, preparation beta is your solvay process. So what you do? You want NaHCO3 and then you will heat it, it will become Na2CO3 and then you will add water. That's simple, we just studied it. But if we don't have baking soda, we just have namak, we just have salt. So what we'll do, we will first make baking soda. How did we made baking soda? We add NaCl, H2O, CO2 because we wanted CO3, so we want HCl and CO2, that's necessary. H we get from NH3. So this is the main basic equation that I taught you how to remember. Okay, Na we get from NaCl, CO3 we get from CO2 plus water, and for H we take NH3. Understood? And we make NaHCO3. Now we want Na2CO3, so we will heat it. We just studied, that is your Na2CO3. Okay, now if we add 10 molecules of water in it, it will simply attach it with the water, making Na2CO3 dot 10H2O. This was very easy. Okay, done. This NaCl is your common salt, NaHCO3 beta is your baking soda, Na2CO3 is your washing soda. Done. Now thus washing soda, sodium carbonate decahydrate is obtained. Then what are the uses of washing soda? It is used in glass, soap and paper industry. Done. Then we have used to form sodium compounds like borax, used as a cleaning agent for domestic purpose. Now this is put inside our detergents. It does not acts as detergent. It acts as washing soda inside the detergent, so it helps in cleaning. It basically turns hard water into soft water, so it is used in removing hardness of water. It turns hard water to soft water. If you don't remember anything, at least write this down. Okay, it converts hard water into soft water. And beta, that is it. Thank you from your Aditi Ma'am. We are done with the second chapter of chemistry, that is acid, bases and salts. And if you are here till the end, I have a very important thing to tell you, that you are doing great. I'm so proud of you and you are already ahead of your class. Make sure you keep this momentum. Okay, subscribe this channel because we are coming live every day. We are giving so many questions, and if you come in live, so many seniors bachas come, right? So you will like hear from them that how much our live lectures meant to them. Okay, so make sure you come because we will do all in my power. Your Aditi Ma'am will do all in her power to make you get more than 95% in your class 10th boards. That's my promise to you, and I want you also to promise that you will work hard. Okay, write down in the comment section that ma'am, I will work hard, and that's how I will know that you have watched the video till the end. Okay, that's it for this video, bacha. Keep working hard. I'll see you in the next. Tata, bye bye.